All right, looking at section 7.2, we're looking at trig integrals here. A lot of these either take the form of powers of sine and cosine or powers of secant and tangent. So initially here we got powers of sine and cosine. Our classic technique is if you have an odd power of either, here we have only an odd power of cosine, chisel away 2 powers at a time until you chisel down to 1 and exactly 1 power of cosine or sine. Because 1 and exactly 1 power of sine or cosine in such an expression will allow you to use u sub just as if that you were dealing with that one true false question on our first test. So utilize sine squared plus cosine squared equals 1 once on the cosine squared, and then you'll be down to just 1 power of cosine, letting u equal sine. Life will be good. Here we've got the odd power of sine. Chisel that away once with sine squared plus cosine squared equals 1, and you'll get down to a single power of sine times 1 minus cosine squared times cosine to the 6th. Let u equal cosine y, and life will be good. The sine y will appear as dy, or as du, and then, yeah, life is good. Okay, here we've got an even power of sine or cosine. So this is going to require utilizing the half angle identity. As the half angle identity plays out in this case, I believe it's 1/2 plus 1/2 cosine 2 theta. And so the integral of cosine 2 theta is that classic cosine kx example. And right, the 1/2 plus 1/2 cosine 2 theta is only so hard to deal with. The 5/2 you can even factor out and then just take it term by term. Incidentally, we're evaluating at bounds here, but whatever, so be it. Once you find your capital F function, you just then subsequently plug in the bounds. So anytime you're dealing with the evaluation of a definite integral, my recommendation would be first, just forget the bounds are even there. Work through, find your capital F. Once you do, plug in your bounds if that's what's necessary. Okay, here we've got a situation with a 1/2 power of cosine, obnoxious as that may be, and 3 powers of sine. Fortunately, we've got an odd power of sine, so hit that sine cubed once with the cosine squared, sine squared plus sine squared equals 1 identity, and you'll turn 2 of the powers of sine into 2 powers of cosine, and then you'll have exactly 1 power of sine left, letting u equal cosine theta. That should resolve itself. Okay, this next example is, well, boy, powers of sine and secant. What's up with that? Well, if I was working with this, I'd rather be dealing with powers of sine and cosine. And so if you take the secant to the 5th and just move those powers downstairs, you could have sine to the 5x over cosine to the 5th of 5x. And dealing with powers of sine and cosine would be nice. In particular, we only have 1 power of sine, so that would be beneficial. Once you move the 5 powers of secant to the denominator, I believe u equals cosine 5x would do it, because that'll take care of all 5 powers of cosine 5x in the denominator. And then the derivative of cosine 5x is what? Just minus 5 sine 5x using the chain rule. And so you can account for that factor of minus 5 as it is through u substitution. So the substitution will work very nicely at that point. All right, next, we've got powers of tangent and cosine. Right, a couple ideas come to mind. So one is, if we write the tangent as sine over cosine, do that. Do that. Write this tangent as sine over cosine, you cancel almost all the powers of cosine. Writing tangent to the 4th as sine to the 4th over cosine to the 4th, you'll just be left with sine to the 4th cosine. Then you're ready to go. That's better than I was expecting it to be. Alternatively, I suppose you could also turn the powers of cosine into secant and then try to play the secant tangent game. But I'd always rather play the sine and cosine game than the secant tangent game. The sine and cosine game seems to be more straightforward. And so, yeah, great little twist on this one. Use tangent is sine over cosine, and then the cosines in the denominator of the tangent will cancel all away and leave you with exactly 1 power of cosine, which is like exactly the size that you need to utilize our techniques, u substitution techniques. It'll be like a question from last test. For this one, right, I'm thinking powers of secant and tangent. You either want to set aside a secant squared, which is going to be a problem here because then you'd have 1 power of secant. That doesn't work really well with our Pythagorean identities, or you want to reserve a secant tangent. That would be the derivative of secant. But hey, that works out pretty nicely, right? Because so just let u equal secant here. You'll have 2 powers of u, and then du will be taken care of with the secant tangent. So this actually isn't that bad for a power of tangent and secant. This one here, how are we going to deal with this? Boy, thoughts. Let's see. Sine over cosine is a possibility, but I kind of just want to. What if we go tangent is what, secant squared minus 1? Secant squared minus 1. Oh boy, am I running a blank here as to how to resolve this? Secant squared minus 1. Let me skip number 8 for a second. Moving on to question 9. You'd either want a tangent and a secant, or you would want a secant squared to be either the derivative of a secant or the derivative of tangent. The tangent and the secant would work because the tangent secant letting u equal secant would work because you'd have 2 powers of tangent additionally to your 1 power of tangent and your 1 power of secant, but the 2 powers of tangent you could chisel away with the Pythagorean identity. Tangent squared is equal to secant squared minus 1. And so exchanging these 2 powers of tangent for 2 powers of secant, or rather, 2 powers of secant minus 1, you'd have just a tangent secant left, letting u equal secant. That would resolve. Down here, again, you either want a tangent secant, but as soon as I say that, if you want a tangent secant, that's great because a tangent secant would leave you with 2 powers of tangent. Those 2 powers of tangent, the Pythagorean identity can exchange for secants, let u equal secant, and life is good. Down here, we've got 1 power of cosine, but that is downstairs. That does not work necessarily well with u sub, but what I'm thinking we might do here is go tangent times sine squared. Turn the sine squared into 1 minus cosine squared. Oh, I tell you what, can we just turn the sine cubed into, oh, that's gonna be, is that gonna be easiest? I think that's gonna be easiest. So if we chisel away at the sine cubed, because this cosine is like minus 1 powers of cosine, which is not 1 power of cosine. That's minus 1 powers of cosine. It's in the denominator. I kind of don't want to deal with that. This one actually reminds me of the one with the square root cosine in front. We want exactly 1 power. The only way to get that, the most straightforward way to get that is to hit that sine cubed with the Pythagorean identity, take 2 of the powers of sine and exchange them for 1 minus cosine squared. And then at that point, you'll be if you have 1 minus u squared upstairs, you'll have u downstairs, and 1 minus u squared over u. There's no quotient rule for antiderivatives, but you can just distribute the u downstairs to each of the 2 terms, and I think both of those resolve. So the only one that I'm not super comfortable with is this tan squared. There's probably something straightforward that does that. Because letting u equal tangent, oh, that's going to be a problem because you'd want a secant squared, but you don't get it. Letting u equal secant, you want a secant tangent. Yeah, let me look up here. This is quite curious here. Number 8, secant. Oh shit. Of course. What function has it? Right. This becomes cookie cutter. That one's obnoxious, but it works. Okay, right. Secant squared, what function has a derivative of secant squared? It's just tangent. You don't even need u sub here. Boy, I was overthinking that one. Well, forgive me for that bit of overthought and having to dive into the solutions to sort that out. But boy, that's not my favorite. Frankly, it's almost too simple. Well, anyways, I don't want to dwell on that during the video and the recording. Hopefully these discussions can be helpful whenever you're working through the trig integrals exercises. Good luck.